Okay, let's continue with spatial joins, and then we'll end up with nearest neighbor analysis. Okay, so again, you can follow using the full binder, student binder with the empty cells, and then the empty cells are also available in the CSC notebook environment. And in the environment, we are in notebooks lesson 3, and we'll start with the spatial join notebook, which looks like this. So I just asked how many of you have, for example, used ArcGIS. So you might remember from there you click join data based on spatial attributes, and then you get a count of features, or then you can join the attribute tables of 2 layers. So as a process, I think spatial joins are familiar, but of course we do spatial joins based on different types of conditions. So again, the intersection, within, and contains. And then it depends a bit if you have points, polygons, and lines, and in which order you give, which is the left table, which is the right table. So it depends a bit then which kind of output you get from these different questions. And indeed, we already covered these relationships in the previous section in this point in polygon and intersect. So we use those relationships then to join data, not just to get the true and false answer, but to actually add the attributes together. So in this lesson now, we'll have to do a bit of downloading data, so we'll take maybe 5 minutes doing that. So we'll have the addresses, again, the very first data set we created today, so the geocoded addresses. And actually what I think I forgot to reveal is that those addresses are actually the addresses of different public transport stations, if you look at how they are distributed in the map. So they are addresses of, let's say, train stations and such. Then we will use population data, which is provided by the Helsinki Region Environmental Services, so HSU population grid 215 grids, which contain the population count. And the data is available for many years, and we will here use the most recent one, which is from 2017. But basically, if you want to do some, let's say, change analysis and such, you have the population data for the Helsinki region from different years available here as a tab format or then shapefile format. So we'll see how we can use that data. So the addresses we should have from the first section in the data folder, addresses shapefile. So that's done. But then we should download and clean a bit the population data. So you can of course do it manually by pressing this download link, but we'll see how we can do the downloading from the terminal. So have you yet used this wget command, webget on the command line? Okay, so has any of you used it before just outside of this course? Sakkenods, okay. So I'll go slowly, and please ask if you don't understand. So we'll need to work in the terminal a bit. So you can open new terminal window, and we can actually organize it so that we can see the instructions. Hopefully, there. I want to have it below. Well, maybe it's better that it's up there. So the instructions are such that we should first navigate to the folder where we want to then end up with the downloaded data. So by default, we are somewhere in the root. So actually, in addition to CD data, I want to first go to CD notebooks. What's inside there? Then I want to go CD lesson 3. what's inside there. There we have now the lesson notebooks, and then now we're up to speed with the instructions, so CD data. Please raise your hand if you drop out at this point, because then you won't be able to follow the rest. And maybe Sake can help if somebody has some difficulties. But basically we want to navigate to the correct folder, so indeed lesson 3 and even into the data folder, and if you there press LS, we should then see the other existing data files. Are you following? Yes? Cool. So then there is kind of this command line tool or package WebGet. You can Google it, but it's an open source simple tool to download data from the internet from the command line. We can even see some help, so usage, we get options, and then the URL. So we need a web address in there. And what is the web address? I actually just copy pasted it from here. So if I would press this link, it would give me this download. It would actually download the data on my machine from the HOASU website. But then I have actually copied that link. You have it here in the instructions. So we want to do, wait, sorry. Zoop, do I have enough space? Let's see if this works. Maybe I'll do it like this because it's such a long address and my screen resolution is not optimal. I'll just do like this. Get some help. Anyway, simple copy paste, which is not so simple in here. I check that the address is correct. Well, there we go. Let's just try it, and then here again, Control Shift paste. It should start the download. Did you manage?
Should we not have a dollar sign?
No, the dollar sign is just indicates that you do this in the command line. So you start from wget and so on. So you do wget and then URL. I'll just come around and see if you're following. So what just happened is that we've kind of called this download link from the command line, and we should now have in the data folder a file called Väestötietoruudukko 2017, so the population grid 2017 shapefile. And we can see it from the navigation pane, and then we can also see it on the command line if we do ls. So Väestötietoruudukko, it's a new file, it's indicated as red. So still it's a zip file, so we want to unzip the file. So without the dollar sign, you can copy paste this piece. So what happens in there is that we have the unzip command, then the file name, and then we add a folder into which we want to store these files. There. So you should get information on your screen that the files now exist in there, and you could still check from the navigation pane that you actually have the file. So it's called then Väestöruudukko 2017.shapefile. Okay, so now we have the datasets, addresses and population grid, right? So let's continue. There's again, I'll have to figure out what is this. It's something related to NumPy. NumPy, so I'm trying to read in the population data that we just downloaded, and maybe I'll check the head. Okay, so I have it in there. Maybe I'm also interested in seeing how many rows there are. Then pop. So there's 5,800 rows, so 5,800 grid cells we have there. And then there's a bunch of attributes. So these are now unfortunately in Finnish. Do you girls have some troubles at the back or no? Not? No.
Yeah.
Okay, let's get you up to. Okay, sorry about that. But indeed, the population data contains columns which are in Finnish. Asukkaita is the column which contains the population count. So the first grid cell has 9 inhabitants, and then the 1, 2, 3, 4th grid cell has 12 inhabitants. And then there's other attributes, but we're mainly interested in the population count and then the geometry of these polygons. So we'll first change, as we have international participants here. So let's rename some of the column names. So pop.rename columns, and we'll rename this asukkaita with using a dictionary into pop 17. So just to make it clear, it's the population in 2017. There we go. And we can check selected columns. So now instead of after the index, we have then pop 17. That's just to make it more easy for us to follow. I guess this we have done also before. Then, as we have so many columns, we want to make it more simple, so we'll subset the data column-wise. So we'll just select this population column and then the geometry, because that's what we are interested in. So we can do that by making a variable which contains the columns that we are interested in. So the population 17, and then geometry. There we go. And then how we select the data based on those columns. So this is the basic pandas approach. So we give the name of the data frame, in this case geodata frame, then the list of the columns we want to select, selected calls, pop head. Let's check the output. Zoom. And what do I have? Is not in index. Aha. So what again? Yes. So here I'm doing something stupid. So I don't know where I got this selected variable name. So I want to. This is also what I could do in place, like we did in the previous example. But here I replaced the population data frame with population data frame with the renamed columns, and then we have the population columns. Sorry for confusing those. And then indeed we run this one. Did you follow? I'm sorry for the confusion. So at the end we have the same data frame. It has still all the rows, len pop 5,800 rows, but only 2 columns. We don't need the rest. Okay, so now we can continue. It's as we are joining data sets, so it's good to kind of clean and strip whatever we don't need before the join, because then we'll end up with a big mess if we have all the columns from data frame A and all the columns from data frame B. And I think this is especially something that's difficult to do, for example, in ArcGIS. So there you need to kind of manually maybe, or if you do it in the simple way, you should manually delete some columns, but here we can do a selection column-wise quite easily before the join. So let's then do the actual join. And now that we're working in a new notebook, so let's read again the addresses into Python. So addresses, file path, we have it in the data addresses.shapefile, location, and then addresses. Now that we have geocoded them, it is a geodata frame, so we can do read file addresses file path and then check the data. So it's a good habit always when you read in something, always check that the structure is as you expect. Addresses.head, because you might make mistakes reading the wrong data, or there might be something funny. So we just check that, okay, the columns are as we expect in the first rows of the data. That's fine. Okay, so now we have POP containing population 2017 addresses that we geocoded. So the actually the transportation station locations. And then one very important thing that everybody should understand is that if we are doing a spatial join, in order to the join to go correctly, the layers need to have the same projection. We can't, or you might end up with a result even though if the projections don't match, but then the output will be bullshit. So let's first check what is the coordinate reference system of POP. That is actually EPSG 3 something, but expressed in this PROI4 format. So if we would just Google this string, I'm pretty sure we'll get the result that it's this ETRS 89 GK Finland. So it's a projection that is used in Finland, for example, by HOASY, and the definition is such. So that's what about then the addresses? .crs. So there we have the EPSG 4326, which is the kind of geographic lat-long VGS84 coordinate system that we got as a default from the nominative geocoder. And you already know, but we can of course check if these are identical, true or false. So we can't do a spatial join between these layers without modifying the coordinate systems. So we want to do some reprojection. So first of all, the layer has to have a defined coordinate system, which both of them have. So if I would type pop.crs is blank, then I would have to maybe Google from the HOASY website what is actually the coordinate of these geometries. So the geometries look, it's this 254, something 6689. So sometimes even by looking at the coordinates, you can tell about something about the coordinate system, and these look like VGS84 coordinates, 24.9, 60.1. That's somewhere in Helsinki, I know, just by looking at the data. But it has to have a definition in GeoPandas, which they both have, but they are different. So let's reproject the addresses according to the projection of the population file, because it's a projected coordinate system, and also as it's a more complex file, it's often safer to reproject the points into then that local coordinate system. So what we basically want to do is to have a new, as an output, a new geodata frame, addresses, which we will replace. We'll replace the old version of that with the addresses to CRS. You learned this last week, but this is now a repetition. And then inside there, as a parameter, we will give the CRS of the population file. So then we'll get exactly the same definition. We could of course do this from Fiona import from EPSG and give the EPS3, what was it, 3, it's somewhere in here. EPS3 3879 as an input, but still then the definition might not be exact. So doing like this, we do it at least like super precisely identical. And then we can check again if the projections now match. And now we get true from this comparison. Okay, so now we have prepared the data sets in a way. We cleaned the columns, there's no unnecessary information, and then the projections match, so we can be safe about doing the actual spatial join. Okay, and how spatial joins are done in GeoPandas? Let's ask from Google. So GeoPandas spatial join. So there is a method called asJoin, which again it takes a left data frame, a right data frame, kind of the type of join. Is it inner, outer, left, right? What is kind of the Shapley method that is implemented? So or the spatial conditions or intersects within contains. And then these suffixes are related. So if the columns have same named columns, so then the left, if there is an index left, or for example, if there was address on the left data frame and address in the right, so then you can specify a suffix that gets added, so you can then identify from which data frame the column came from. So this is the tool that we're using. So basically, we'll end up with an output called join. So that's the output that we'll get, and then we'll call the GeoPandas join like this. So gpd.spatial join, sjoin. Then the left data frame will be, so here the idea is to attach population information to the points. So we'll find the population grid within which the point is, and then link the population information to that point. So basically to the public transport station. So addresses and population grid. Then how we want to do this join, so we want to do an inner join, which means that then all those records that don't have a kind of common geometry relationship are excluded from the output. So if there's one point that is in Estonia and our grid is from the Helsinki region, then that point will be excluded, or if the grid extends beyond where the points are, then those grid cells won't be in the output if we do an inner join. Inner, and then the option, so we do a within, so points within population grid cells is what we're looking for. And then join.head, let's on the fly see. So here we're make spatial join, check the output. Okay, so the result looks like this, or at least the first rows. Of course, we can check length join. So we have 32 rows in the output. So let's check, was there length addresses? So there's two addresses that have been dropped out from the result. And then we have the IDs, the geocoded address, the original address, then the geometry, so that's the geocoded point geometry, but then we have two new columns which have been joined from the population grid, so index right, so the grid cell index, and then population 17. So there is a specific grid cell within which this point was located, and the index of that grid cell was this one, and the population of that specific cell near Itämeren Katu was 501 in 2017. that's the kind of output we have from this kind of point in polygon based spatial join. We can save that result for further purposes. Maybe we'll do data addresses. So the dataset contains the address points, but with population 17 information, and then it is actually now in EPSG 3879.shapefile. So I sometimes do also this, that add, if you do intermediate outputs, it might be nice to tell yourself what is actually the point of this layer. So it's addresses with population information, and it's projected into this projected coordinate system. I hope this went now correctly. And then join to file out FP. Okay, so then in the data file I have these addresses with the population information. I guess that's clear. And then finally, let's plot this data and see a bit what kind of information could we derive from this spatial join. So again, let's import matplotlib that we can make a nice plot. .pyplot as plt, that's always difficult to type in. Plot the points with population info. Okay, so what do we want to plot here is the join. So the join output dot plot. Of course, we could just do that as a warm-up. Plt tight layout, or you could do plt show, I guess, as well. Does it give me anything? It might want a column. There we go. So this kind of syntax, it just plots. It takes the it notices that, okay, I have a geodata frame. You want to plot the coordinates. There we have it. So indeed, as I mentioned, these are addresses of specific public transport stations. But then we can also plot the attribute information based on specific column. So we can add population 17 as the column. I think this won't yet change anything. So still, well, it gives some default coloring now based on the population or the distribution of values in that column. But we can also then define how this is rendered. So we can give a color map parameter. There's a bunch of default color maps. One of them is called reds. So we'll put a red color scheme in there. Let's see what that does. So now there's some kind of a red. So intuitively I would read this so that the lighter the red, the less population there is close to that station, and the more dark, the more population there is. So that's quite logical. These are located somewhere in the city center. Then we can still add marker size. Let's try 7. Okay, I'd like better the bigger one. Let's try 12. Anyway, but you can, with the marker size, you can play around with the size of the bubbles. Let's see, then put a bigger one. At least on my screen, I can't really see anything. There we go. And then basics of kind of cartographic mapping or thematic mapping, to be more exact. So we have some kind of a classification scheme that decides where are the threshold values for low and high high values, so we can also define that in here. So with the parameter scheme, there's different options, but one of them is, for example, quantiles. So the algorithm puts equally as many observations. Quantiles. So it divides it into equally sized partitions. We can try that. So the colors should change a bit. Okay, I get some errors, but let's ignore that. So now there's more stations that went to the kind of high population category with this classification scheme. Let's check what these warnings are about. There's always these packages are being updated, and then Python warns that some, for example, some functionalities are being deprecated. Then finally, this is more, we're plotting this data for kind of data exploration purposes, but of course, as geographers and cartographers, we might want to have a legend explaining what does dark red mean. So you can also add a legend or explanation of the content. So legend, it's a Boolean parameter, true, false. So then by default, there is this. So here, from here we can see that the darkest red is up from 631 inhabitants close to the station. Then by modifying the scheme, we can have different kinds of classifications of the data. Then of course we could make this bigger, we can add background maps and such, but those we will learn in a few weeks then. But this is now the end result of this point in polygon based spatial join query. And you'll get to practice this a bit more in the exercise. So think about when doing the join, so this S-join thing, so the order of these parameters matters. Which one is the left one? Which one is the right one? Is it the points or the polygons or vice versa? And then that affects which type of spatial relationship are you asking? Is it points within polygons or polygons within points or intersecting polygons, or what are you actually? So try to write it down in English. What are we actually asking from this function? Do you have any questions? No. If not, then we'll continue to the last bit of the lesson, which is the nearest neighbor analysis. Again, it has its own notebook available for you. So let's go this through. You'll get. So in the lesson 3 folder, the bottommost notebook, nearest neighbor analysis. So basically, I'm kind of tempted to draw again. Sorry for everybody who's looking at the video. I don't know if you can actually see these drawings, but basically, I'll just draw it in here. So we have some points. These can now be, let's say these are grocery stores or something, and this is my home. Or it could be a set of points, or it could be a set of polygons. So the basic question is that which one of these points is closest. So we have some origin points and destination points in a way. So which one is closest? Then we could also have, we won't do this today, but there can be a polygon and another polygon or set of polygons, and then the algorithm will find which is the nearest point in these sets of geometries. So we have origin set of geometries, destination set of geometries, and then the algorithm we're using from Shapley finds the nearest point in those sets of geometries. It's that simple. Maybe, but indeed, nearest point Shapley function is what we are using through this whole tutorial, and indeed it returns a tuple of the nearest points in the input geometries. Here, just to give a simple example, we have some input data ready. So there is one origin point, so it has x and y coordinates. And then we are on the fly defining 3 destination points. So first, dest point 1, dest point 2, dest point 3. We can read those in the memory. Dest 1, for example, then looks like that. So you can indeed define several variables in one line of code if you like it. It might be more clear to have them also in separate lines. So we have 1 point and then 3 points. And the question is which one of those destination points is closest to the origin point. So technically how this is done in order for us to use the Shapley nearest point function is that we have to kind of we have to make this set of geometries out of the separate points. Just kind of in order to comply with the requirements of this tool. So we have the origin and 3 destinations, so we could make a variable destinations, which would be a multi-point made out of those 3 points. So we have the dest 1, dest 2, dest 3. There we go. So we have a multi-point object which contains those 3 objects. So we can give it as one input parameter for the nearest points function. And then so if we use it, we will get an output, and the output you'll soon notice will have not only one geometry but many. So we'll call it nearest geoms, so nearest geometries, the nearest from the left one and the nearest from the right one. And we'll call this nearest points function from Shapley. And as an input, it takes the origin points, or the origin point that we have, and then destinations. That's what we have. Oring. It's not orange, but it's orig. Okay. I think it passes, and then maybe we want to check what it actually contains. Nearest geoms. Okay, so we have a container with, or I think it's a tuple type nearest geoms. So it's a tuple, I think, yes, it's a tuple containing two geometries. So maybe we'll quickly have a look at the Shapley nearest point documentation. So why do we get this? The Shapley user manual. To get a bit more explanation. Nearest points. So in Shapley, this is a bit maybe not the most clear example, but indeed did we actually? Yes. So we have in the first ready-made cell, we have imported the nearest point function. That's why we can use it. And in this example, they are putting in a triangle and a square, and then the function finds the nearest points in that triangle and then that square. We're doing this a bit more simple way with a set of points, or 1 point and another set of points. But indeed, what the function by definition takes as a parameter is 2 sets of geometries, and then it returns a tuple of the nearest points in the input geometries. That's what it does. So let's still have a bit closer look at that. So how we can access contents of the tuple. So we have the nearest geoms at position 0. There is something. So let's print that. Move that up there. Print contents. Okay, so we have point. So this is from the first set of points, and there we had only one point, so it's the point itself, basically. That's quite simple. And then we have this at position 1, so the other geometry, then it's 0.0 and 1.45. So then it was test 1, which was closest to the origin point out of these sets of out of the set of geometries that we gave as an input. Yeah, is this somewhat clear? I guess yes. Yeah, it's quite simple with these individual objects. But then, how can we actually use this tool in GeoPandas? And at least according to our knowledge, it's not yet implemented in GeoPandas in the similar way as within contains these sorts of things that we can just type geodataframe.within and everything works quite easily. So for these purposes, this is a function written by Henko, which we will use here to apply the nearest points functionalities into our addresses and district area datasets. So we, for example, here we'll figure out which one of the points, or which way, let's check which way it is, but we will generate centroids for the districts and then look at the relationships of the district centroids to the points that we have geocoded, to put it simple. So you have this ready in there that we avoid typos, but let's discuss a little bit what this function consists of. So we are defining our own function called nearest that we will then apply on each row of the geodata frames that we have. You used the apply method last week, right? I know it's a very useful thing. I nowadays myself use it a lot. Instead of doing this dataframe.iter rows, I often do things with the apply method, but it takes a bit of practice and a bit of repetition to understand. So don't worry if it's totally not clear. But the point is that we define a function that we then apply to each row of the data. And here we define a function that will treat the geometries then of each row.
I think we might not have It's in the
Okay. Okay. So then I'll go slow and let's then see if we still want to return to this. Okay. Let's go through the example and then please ask questions of what is not clear. But this is kind of an alternative for the approach of doing for index row in data iter rows, take a row, column, do some calculation based on that value, and then data.lock, put the value in place again. So instead we can kind of define a function which then we apply on each row, and you'll see a bit later how that's done. But first of all, let's just think about the function. We want a function that takes each row, so in order for us to access each geometry of the data frame in there, and then we will need some kind of in the previous example we had this multi-point geometries. So in this example the origin points will be the geometries of the data frame that we are handling, and then the destination points will be a collection of geometries retrieved, for example, from another data frame, but those we need to give kind of as a package. So that will be the geometry union. Then the function will take the left data frame, the right data frame, you'll see soon why. Then we can also define which column contains the geometries that we want to compare from the left column and from the right, or data frame 1 and data frame 2. and then a source column, which is optional. And then what is actually done inside, so this is the key component in there. So we are using the Shapley nearest points function. And inside there, this is something that should be then quite clear. So we have, for that row where we apply this function, we take the geometry from the specified geometry column and compare, find the nearest points. There again, we'll have only the one if it's a point file. So the one point from that row geometry column, we will compare to the geometry union. So then we'll have a bunch of points or a polygon or something else. So this will be done then when the function is applied, and this piece in here, as you saw previously, so if we would call nearest points at position 0, it actually returns the origin point, so the original point in the row, but we actually want to get out of these points in the geometry union what was the closest to that one. There. And then that we will put, so well, this is a bit difficult to explain, but this will return true or false, based on which we will then get the kind of access the corresponding value from the source column, or then all the columns in the target data frame. This is a bit complicated. I think we just need to run it and do it, and then try to see if we understand it a bit better. So, function definition. Then we have GeoPandas. Again, these weird warnings. I can figure out what they are about. Input files. So we have the district dataset from KML file, addresses, and again, as we're now in a new notebook, we need to enable the KML reading, which we learned when doing the point in polygon processes, and we read this into geodata frames. So So first of all, we need to have, so we'll apply the function on one of these datasets, and from the other one we want to create this kind of big collection of the geometries, and that is called Unary Union, so we can call the variable also as such. Data frame 2, so our data frame 2 is then the points, so we'll do kind of a multi-point from, sorry, Unary Union, and then print this Unary Union. Okay. So what happens here is just we take all the geocoded addresses and put them together so that we can compare those then to the source or origin points. And then what we will at the end compare are the centroids of the points. We could also do a comparison between the polygon, but then the result will then mean a bit different things. So here, to be precise, we are comparing, we're finding the closest addresses to the centroid of each district. So then we can add a column to the data frame 1, which is our districts, called centroid. Oops. Centroid equals data frame 1 centroid. So this is something that is implemented in GeoPandas readily. We can just call data frame 1.centroid. right. Getting tired. There we go. And then we can check df1.head. So now in data frame 1 we have the geometry column, which is the GeoPandas geometry column. So if we plot the data, this will be used as the geometries. But we have another column which contains Shapley geometries, which is the centroid column. And so indeed this is the calculated centroid of each polygon. And that is actually what we want to then use in the nearest neighbor comparison. Okay, so then how we are then applying the function, let's just go ahead with it and see what happens. Nearest ID, so we'll, as an output, indeed, we want to find for each district the ID of the point that is closest to the centroid of that district. And in a new column, nearest ID, we will store the ID of that station, basically, or that address. So then we will do df.apply. Let's see, data frame apply. I hadn't prepared any materials for teaching this, but let's just see. So basically there is this functionality, pandas dataframe.apply. You can read more about it here, but as the first parameter it takes the function. So you need to have some function that you apply. Axis, so does it apply it column or row wise, and other parameters. But the key here is that it's a function to apply to each column or row. So you can think that it works in a more efficient way, but you can think of it as this data iter rows, and then for row do something. So that's what happens. So it takes one value from each row, does the calculations based on the function, and then continues. So we have dataframe.apply. Then our function was called nearest. And often when you call functions, you would call nearest and then parentheses and then input parameters. But here, how you set the parameters of the function is then after inside this apply command. So our long and monstrous nearest function had all these parameters. So we could actually, sometimes it's a good idea to do like that you copy all the parameters in order not to forget any of them and not to mistype them. And then I paste them here, and then we'll start modifying accordingly. So our nearest function wants input parameter geom union. And what is that? We have the origin points are in data frame 1, and then the destination points are these unified address points, which are stored in the Unary Union. So our geometry union, to which we compare, is the Unary Union. Data frame 1 is data frame 1. Data frame 2 is data frame 2. Geometry column in the left data frame, we could have geometry, and you can of course try what happens, but actually we want to have the centroid column. So we want to compare the centroid to the set of points. So it's defined in there. Then geometry column 2, so in the data frame 2, that is well, it's geometry, so we can have it there. As it's also set by default, we could also delete this from here, but I'll just leave it in there just not to confuse you. Then the source column, we will want to have the ID of these addresses attached. Okay, there's still one thing that's missing, but I'll run this. I will get an error, but then maybe that error will explain what I'm missing. Okay, so that's at least one error, data frame 1. what else? So often in the error messages, the last line sometimes is useful, but here it's actually not. What I'm missing here is what we saw in this pandas data frame apply is the axis. So the axis means the axis along which the function is applied. 0 would mean that the function is applied to each column. So it would take the columns as pandas series and apply the function to each value in there. Or, well, column-wise anyway. Or then 1 apply function to each row, and that's actually what we want to do. So you remember we always do this index row in pandas iter row. So for each row do something. But by default, this apply does it for each column do something. But we don't want to do it column-wise, we want to do it row-wise in order to access then specific values from each row and then to store the output in an additional row. So we still need an additional parameter axis equals 1 so that we apply the function to each row. No, oops. Okay, no errors at least. Let's then see what we actually have. Data frame 1 head. So here we have created a new column where we have then the ID of the address point that has been nearest to the centroid. And how it was calculated is all defined in this function, which I maybe didn't explain the best way possible, but we could still break it down and also maybe write it in a bit more simple way. But basically when the function goes through, it applies for each row, it takes the geometry column, so this will be the centroid of the first, in the first iteration, the centroid of the first row, then all of the destination points, so all of the addresses, and then this one will return one value, which will be one out of all of these geometries, and then it will compare, or it will detect the rows, which will be eventually probably one row because the coordinates are unique. So it will give a true-false mask out of the result of this, and then based on that mask from the source column, this will return, in our case, as we defined the source column as the index, the value. It returns the value, and then in our case it places the value kind of data frame lock on that row when we apply the function to the nearest ID, and we end up with the ID. I think that's the best explanation I can give, and you can then try to reapply this method or create your own method in problem 4 in the exercise. So I'm quite amazed that we are actually in time. I know you might have questions, but I think, well, if you have questions, please ask about this, but I'm pretty sure half of you are super confused. Maybe? No? Yes? Dean?
Can you just explain diagrammatically why you're using this centroid?
Okay. Let's try to see. Of course, it's just I guess the real answer is that we just want to make it easy here. We want to compare points, but we have so this is our district, and then we have these. We have the address points. Our address points. So that's the centroid with the star, and the address points are here. So then, of course, then we, instead of, so what we do here is that we make a multi-point object of these points, and this is the kind of origin point or the left side, and then all of these are the right side, and then it compares, it finds the nearest, and then, aha, this is the one, and it returns a tuple with this and this coordinate. If we had put in the polygon geometry, then we would have this the polygon geometry here, and then, well, maybe a full circle. Let's pretend then this is now our district. It's easier to explain than the thing. So then it would find, maybe the result wouldn't be so meaningful because we would have points maybe inside and outside the thing, and how this would then work if we have the polygon as the left side in the nearest points, and then the multi-point objects, all of these in the right side. So then the result might be something like this. So then it would be this point, or it might be something like this. So it would just give us the point that is closest to the border of the polygon, which might not make sense. It might make sense if we have a setting where we know that all the polygons are points are outside the polygon, and we want to see which soldier is closest to the castle, whatever application you have. Does it help a bit? Yeah. Okay. Okay. Then yes, let's wrap up. Whew. Yeah. Did you get some of this? Hopefully. Maybe. Yes. Yeah. Good. Yeah. I was a bit afraid of this section. So we went through all the materials. You have them there. Exercise 3, the GitHub Classroom link is not yet there because I had help from Oyedayo to check if we have any typos and stuff, but you can already see it from here. I'll update the GitHub Classroom link straight after this lesson. So we have 4 problems related to directly what we just went through. So in the first problem, you actually have to create the input text file yourself. So create a similarly structured file as we use today, but the file should have 1, 2, 3, 4, 5, 6 rows with addresses to shopping centers in Helsinki. You can just Google the addresses and put them in a semicolon separated text file with columns ID, name, and address. In there, then use the nominative geocoder to geocode the addresses, and then join again. You have the original input, then the geocoded result, join the name information and the IDs in there. So that's kind of the same thing as in the lesson, but with different input data. And then kind of the rest, problems 2 and 3 will have this kind of a case study of figuring out how many people live within a certain buffer zone outside of the shopping centers. So we'll do some buffering around the shopping centers. Then we'll again use the population data. So the population grid data that we just managed all to download. And then we'll do a spatial join to figure out, so you'll then have to think if you have buffers and population grids, do you do within or contains, and which way you join the data in order to get the sum of people living within the shopping centers. Maybe I'll do one last drawing. So you'll have a shopping center here, I don't know if you can see these, and then you'll have these grid cells inside. So then the result will be the sum of populations in these grid cells, basically. That's what's in there. Until problem 3. So you should make a code that prints. So in problem 3 and 4, the instructions are a bit more, they are structured, but they are a bit more loose because, of course, it's nice to have these like well-structured notebooks, but then it also might restrict your creativity. So in problem 3, we have just this list of bullet points of things. So feel free to create. You don't have to write everything in one code block. You can create more code blocks there and test your code and make it work. And then in problem 4, does this work? Ooh, you'll then get to revisit this nice nearest points functionality. So the idea would be, we ask you to find the closest shopping center from your home or work. Of course, if you don't want to put your exact home location there, we don't care, you can put whatever. locations, but basically you'll have an input text file with 2 rows, 2 locations that are maybe important to you, and then you'll find nearest shopping centers to that one. So that's it, and I'll indeed publish. I can even put the link to Slack now and then. Let's maybe do that. I actually have it in our hidden channel in here. So if you're super eager, you can start working instantly. GitHub Classroom link. Yeah, but there's always these baby mistakes in the exercise folder, so we try to fix those before everybody clones it. Then it's more difficult to fix. Okay, thank you for attending. And if you have any questions, you can stay here. And we'll see you tomorrow in the practical session. So I could demonstrate the way from exercise 2 how you can make it more faster, this iter rows thing, if you're interested. Thank you.